theories of this category. That's a lattice. The torsion theories form a lattice. So that this torus rep is a lattice. I abbreviate it by top. Now you see, from that lattice is replacing the topology. And in the commutative case is the Zariski topology. That is what happens here. So you have a canonical. Now you know where the Zariski topology comes from. You have a canonical topology. If you think I take a representation category and I take the torsion theories of this representation category, that is a topology. Well, it's a lattice and it generalizes a topology. And it is the right topology. It is, for example, classically the Zariski topology. Okay, so there are two ingredients. In fact, there's only one ingredient. Choose a Grothendieck representation of your category that you're looking at. If you do the graded rings and you have graded morphisms and everything then you take here the torsion categories that are graded torsion theories. And you only have to, I will do this on the next slide I think, you have to take care of the zero. So let's go to spectrum.
So what is exactly, how should I go with the torsion theory?
Yeah, so should I do this by an example or do you want the abstract?
I want an example.
You want an example? So, okay, get rid of my devil instrument. So for example, you take a commutative ring to start with, right? And you take an ideal in this ring. And then you take something which is a kind of filter, Gabriel filter, if you know what it is. But this is then supposed to take all ideals L that contain a power of the ideal. Everything that contains a power. Then you take the C modules, is your category. And then to every module you can associate a torsion part, which let's call it kappa I of M, as all the elements in M in M, which are annihilated by an element of that filter. So in other words, annihilated by a power of the ideal.
Yeah. Do you get more than a power of the ideal? Can you get more than just annihilated by power of the ideal?
Yes, well, yes.
I mean,
Well, if the ring is Noetherian, you don't get more. This is an essential point, really. The algebraic geometers, they hate non-Noetherian rings, right? Michael Arkin said at a certain time, they should have killed all the students of Gilmer. Because Gilmer was doing this commutative algebra with proofer domains and almost Dedekind rings and almost semi-hereditary Dedekind domains. And the real geometers don't like that. But, in fact, I'm going to say at a certain moment in a non-commutative space, we don't have enough points. And this will be a necessary condition. If you have enough points, the space will be commutative. But even in the commutative theory, you don't always have enough points. I was acting like a geometer at that point, and said, yes, we construct points and so on, but these people always work with affine rings over a field or with Noetherian rings in the scheme theory. And if you work with non-Noetherian rings, that is not true. You don't have enough points even in the commutative case. So it's not so strange that in the non-commutative geometry, we are saying that, okay, we have to invent something about points. But even in the commutative case, that is a problem. But if you hide the problem, then you don't see the problem, right? But in fact, the difference, I can tell you, so I didn't say C is Noetherian. So there's another filter, let's call it RAD. I, which is, how is it again? Oh yeah, it is two-sided ideas because I'm commutative, such that the radical of L contains I. So it's almost the same, only that the radical is not nilpotent over the ideal. It's nil, but not nilpotent. So in the non-Noetherian case, there is not a power of this in that. Right? In the Noetherian case, the radical in some power. So if this is in the radical, then some power is in L, right? In the Noetherian case. Otherwise, it's an elementwise condition. It's nil, but not nilpotent. So if you're in a non-Noetherian ring, these are different. So there are two torsion theories, two localizations. They are different, but they define the same prime ideals. They're the same. They correspond to the same set in the spectrum. Because if a prime ideal is here, it just means that it contains I. If a prime ideal is here, it just means it contains I. So they correspond to the same set in the spectrum. So you would think, ah, that's the same thing in the Z. Well, it's the complement is the open, otherwise it's the closed, of course. So they correspond to the same thing in the spectrum, but they're different localizations. In the thing I present, the topology enters as the localizations. And so it is a theory which generalizes the theory of schemes in the sense that you look at a bunch of localization functors glued together by some topological-like conditions. And that is the idea of non-commutative geometry. So that's why I have a sort of book, a pure small book with a lecture note, called Virtual Topology and Functor Geometry. So when I throw away all the algebra and the geometry and the category theory, then what I have left is that, a bunch of functors that sticks together well. You apply this bunch of functors and that's kind of sheaf theory, localization theory. So, but you see, even in the commutative case, if you have a non-Noetherian ring, there are two localizations and they correspond to the same set in the spectrum. In the prime ideal spectrum, if I now define the spectrum differently and I want to look at the spectrum as the prime localizations, then I get more, even in the commutative case. And if you talk to any algebraic geometer, he will think that the prime spectrum and the torsion spectrum is the same. Because if C is Noetherian, then that is true. Then these are the same. And in any case, you can see that these filters depend only on the radical ideals, on the prime ideals. So if something is in a prime ideal, or it is not. So the whole idea of scheme theory and the prime ideals acting as points of the topology is there, but is for them very connected to the Noetherian assumption. So I don't have to assume that, but I don't care to assume it. I mean, why not? Most of these non-commutative rings that I want to apply this non-commutative geometry to, they are Noetherian, right? I will show you a list. So that is not so essential. Therefore, it is not unreasonable to say in the commutative case has enough points. The non-commutative case, you never have enough points unless it's commutative. But this is a kind of warning that if you would like to do geometry for non-Noetherian rings, you have to go away in the non-commutative direction already. In a sense, that is an intermediate step. Okay, so there is another topology which appears very naturally, which is the same in some cases but different in others. There is a spectrum that you can define, like the prime ideals or the prime torsion theories. The prime torsion, so the torsion theories or the localizations, they form a lattice, and you can take the irreducible elements for the intersection, like the prime ideals. That would be a prime torsion theory. And in the Noetherian case, again, you can prove that every torsion theory is defined by prime torsion theories. It's a collection of prime torsion theories. So it's just really a kind of spectral thing. And there is a canonical topology of it, which is called the gen topology, gen for generalization, nothing to do with genetics, I think. I'm careful nowadays. Sorry.
Could you maybe show the overhead slightly in the picture?
Is it deforming? I thought it was my eyes. I thought it was my eyes, the beer last night. So you have it too. It's okay? Okay, so what you do, you take all these torsion theories, you look at the prime spectrum, and an open in this gen topology is just in it everything, all primes bigger than a given element. This you can express, if you do that here, you would find the primes not containing the ideal. That everything bigger than kappa I. So that the gen topology in this case is again the Zariski topology. As I said, yeah. Okay, so there is an observation here. Why to go to the spectrum at all? You could just do the sheaf theory on that top, the torsion theories of the representation space. That's a canonical thing, so we can do the sheaf theory there. But the reason is, classically, why you go to the spectrum? Because you do geometry that is visible on points. This is the place, as I say here, that is exactly the place where you put in the philosophy that all the geometry is visible on